Okay, I'm going to go ahead and get started. So before we jump into the lecture, I just want to review a little bit on what we talked about in day one. So mostly focused on what you need to provide before you can do calculations, which includes all of the elements, where they are in space, including the hydrogens, with a reasonable starting structure, that you have to provide the overall charge and know the number of unpaired electrons in your system. And if you don't know the number of unpaired electrons, you can sample the multiplicity by running multiple calculations and comparing the energetics. Okay, so this morning's lecture is going to focus on the different levels of theory. Okay, so for the different levels of theory, we're talking about the form of the Hamiltonian. Okay, so yesterday afternoon, we talked about basis sets, which describe the mathematical formula for the wave function, the atomic orbitals that are used to make the molecular orbitals. Okay, so this morning's lecture is going to focus on what the form is for this Hamiltonian operator that gives us the energy of the system and optimizes this wave function. Okay, so just as a reminder, we have substantial approximations that are made in the Hamiltonian. Okay, we spoke about the fact that it ignores this thing called relativistic effects, which is very important for the heavier elements in the periodic table. Okay, but we do incorporate relativistic effects by including something called an ECP for those heavy elements instead of using an all-electron basis set for the wave function. We neglect coupling of electronic states, and more importantly, neglecting the coupling of electronic and nuclear motion, which is the Born-Oppenheimer approximation. And just to recap, the Born-Oppenheimer approximation, the electrons are moving so much faster than the nuclei that we make the assumption that the electrons see static nuclei that aren't moving. Okay, so it's sort of an instantaneous. So we can optimize the wave function, and then we move the atoms. And then we optimize the wave function, then we move the atoms. So their motion is decoupled. So what does this Hamiltonian look like? Okay, so this is a very generic equation for the Hamiltonian. Okay, and this is for a many electron Hamiltonian. So we have a kinetic energy term here. Okay, for both the nuclei and the electrons. Okay, and that's shown here with a capital T, nuclear kinetic energy, electron kinetic energy, and then we have a bunch of potential terms. Okay. So this term right here is the potential energy for the nuclear electron attraction term. The nuclei are positively charged, the electrons are negatively charged, so we have an attractive term, which is why it has a minus sign in front of it here. Okay. And then we have the electron-electron repulsion term. The electron-electron repulsion term, they have the same charge, right? They want to stay away from each other. The electron-electron repulsion term is the one that the calculation spends most of its time trying to solve. This is the computationally intensive term and the one that is hardest to get correct. Okay, and then we have the nuclear-nuclear repulsion term, okay, or interaction term. Okay, so normally when these calculations are performed, the terms are split up and you have a nuclear component and an electron component. Okay, and this is what the Born-Oppenheimer approximation lets us do. Okay, so we can have a nuclear component, and then we can have a 0th order component, and then we can have a 1st order component. So we have the nuclear split up here. We have nuclear for kinetic energy, nuclear-nuclear repulsion. And then we can couple together or bundle together the electron kinetic energy and then the nuclear electron attraction term. And then lastly, the difficult one, which is the electron-electron repulsion term. Okay, so this is the one that is the most difficult and most of the time is being spent trying to calculate. Okay, so I need to talk a little bit more about the form of the wave function. So like I said, yesterday afternoon, we talked about the form of the wave function by using these basis functions. And in Gaussian, it uses Gaussian type orbitals, which is the e to the minus zeta r squared term. It was a linear combination of atomic orbitals. Okay. But we can't just use a linear equation overall, otherwise we would violate some of the quantum rules. Okay. So instead of just having a single linear form, it's put into a matrix. Okay. So that's what this Slater determinant is here. These are the different orbitals. Okay. This is spin up, this is spin down. So orbital 1, okay, spin up, spin down, up through the n electrons. Okay, occupation of the orbitals from electron 1 up through n electrons, and it's put into this matrix form. So we're not going to go into the details as to all of the quantum rules, again, outside the scope of the short course, but it's important to point out that it uses this Slater determinant, a matrix form for the wave function, which satisfies the rules of the electrons have to be indistinguishable, and the overall wave function has to be antisymmetric. Okay, so there's actually multiple ways of doing this, but this Slater determinant will always make sure that these rules are satisfied, and it is a good way to go forward to do these calculations computationally on the computer. So that's where we end up with all these matrix multiplications. Okay, so a lot of the quantum codes are still written in Fortran because historically Fortran was really, really good at matrix multiplications. Okay, and that's why I get this question all the time is, why are these codes in Fortran? Why are a lot of these codes in Fortran? It's because they were superior in matrix multiplications. And most of the computation is looking at matrix multiplication, integration with matrix multiplication. Okay, so let's talk about our lowest ab initio level of theory, Hartree-Fock theory. Okay, so this is the form of the electron component of the Hamiltonian. We have our kinetic energy term, okay, we have our nuclear electron potential term, and then the 2 electron interaction term, okay, which you saw on the previous equation. So it's the way that it determines this potential, this electron-electron term. That is the term that is generally varying for the different levels of theory on how it treats the electron-electron interaction term. So in most of these theories, it will separate out 1 electron interactions and the 2 electron interactions. Okay. For the Hartree-Fock theory, I'm looking at the potential for electron 1 overall. If you take electron 1, you can sum over all of the interactions with the other electrons. Okay, so you can integrate over the density of this 1 electron, okay, electron 1 with the density of the other electron. You can integrate over all space for that. Okay, and then you just add on the electron nuclear interaction. Okay. So the consequence of this equation for Hartree-Fock theory, the way that it's listed out, is that electron 1 sees a smeared out cloud of the other electrons. Okay, so it's an average effect. Electron 1 sees this smeared out cloud of the other electrons. Okay, and that's how Hartree-Fock theory treats the electron-electron interaction. Okay, so overall, it gets a bunch of 1 electron Schrodinger equations. You have the kinetic energy term, you have the overall potential for electron 1. This is the spin orbit for electron 1. You get the energy of the orbital for electron 1 and the spin orbit back again. Okay, so a little bit more detailed equations for the Hartree-Fock eigenvalue problem that needs to be solved. Instead of having the Hamiltonian, they specifically put in the Fock operator. Okay? And this is over all of the orbitals. Okay, orbital 1, orbital 2, and this is the energy of the orbital and the spin orbit back again. Okay, so for a closed shell system, you can write the equations look like this. Here's our orbital energy. We have our 1 electron Fock operator, our 1 electron Hamiltonian operator, and then summing over all of these 2 electron terms. Okay, so the form of this 1 electron operator is just the kinetic energy of that electron and the electron nuclear attraction term. Okay, so these are very fast, the 1 electron integrals that it calculates. The Coulomb and exchange integrals are the ones that it spends most of its time computing. So the Coulomb integral is a very intuitive integration, or a very intuitive interaction, sorry. The interaction is the electrostatic kind of interaction. So you have the electron is the same charge, and so it wants to stay away from each other. Okay. The exchange integral is a purely quantum effect. You get a stabilization out of the indistinguishability of the electrons. So if you exchange the electrons, it's actually a stabilization term. Like I said, this is a purely quantum effect and doesn't have anything at the continuum level that is tangible for us to relate to. Okay, so the 2 electron integrals, like I said, are the one that it spends the vast majority of time computing. A little bit about this notation. Let's see, I realized I didn't mention it. When you integrate over all space, instead of writing the integration like this, you can use this bracket notation. Okay, so here is the front of the integral, and here's the back of the integral, and this is it operates on the thing in the middle. Okay, or sorry, this is the operator in the middle. So if you have both the bra and the ket, then you're integrating over all space. So this is just shorthand notation for integral and integrating over all space. Okay, so one thing that I want to point out with these equations is here we have the energy of the orbital, which I mentioned on the last slide. If you rewrite this, you get the Hartree-Fock energy for the system. Okay, and that's going to equal 2 times summing over all of these 1 electron interactions. Okay, and then a double summation over all of the 2 electron interactions where we have the Coulomb and exchange interactions plus the nuclear term. Okay, the nuclear potential term. We can rewrite this where we have, instead of the 1 electron operator, we substitute in for the orbital energies. So here we have 2 times the summation over the orbital energies. Now we're subtracting off the 2 electron terms, okay, and the nuclear component. So what's important about this is that the overall energy of the system is not a sum of the orbital energies. And this is a very common misconception. A lot of times I will see people that will run calculations, and then they will determine whether or not a system, one molecule, is more stable over another based on the highest occupied orbital energy. Okay, and that is not a good assumption. Okay, that is normally not correct, because it's more than just the orbital energies. You also have all of the 2 electron interaction terms, okay, that go to the overall energy of the system, and the nuclear terms. Okay, so you cannot just look at the orbital energies to determine stability of the molecule. Okay, or to determine the stability of the molecule. The orbital energies can be useful for other things, but not for the overall stability. Okay, so we're not going to go through this in detail, but I want to show you this slide because it is important to understand that this is a self-consistent procedure. Okay, so on the first day, I showed an iterative process for optimizing the wave function and an iterative process for optimizing the geometry. Okay, and this is because of the way that the Hartree-Fock theory equations are solved. Okay. Since this is a set of nonlinear equations, it is solved iteratively. Okay, it doesn't have an analytical solution. So we have this Fock matrix, we have the molecular orbital eigenvalue matrix, then we have this thing called the overlap matrix. And the overlap matrix is how much those molecular orbitals overlap. Okay, so it's not diagonal. So to solve this, you have to transform it so that you can get something that is diagonal. And then you transform it back to its original state. Okay, so this C matrix here, this is the coefficient matrix of the basis set, right? So remember those coefficients that are being optimized, the A, B, C, D, E, okay, that goes into this matrix. Remember, it's a matrix because we're using, get back to here, because, oops, I went too far. We're using the Slater determinant, which is a matrix, okay? And you have all of those coefficients that are in there. Okay. So like I said, to solve this, you have to get S to the identity matrix. It's diagonal, and we only have values on the diagonal. So it goes through this transformation process, and then it brings it back, and then it compares it. Okay. And that's why we have an iterative process for Hartree-Fock calculations. And this is going to be true for density functional theory and for many of the other ab initio theories, okay, levels of theory. But that's why it's self-consistent. So you have to have this initial guess for the coefficient matrix, and that's why your starting geometry is so important, the quality of your starting geometry. Because if the quality of your starting geometry is poor, your initial coefficient matrix in front of the atomic orbitals is going to be really bad. And it's not going to be able to converge the wave function in this iterative process. Okay. So that's where the iterations come in, and that's why it's self-consistent, because we're solving these non-linear Houton equations. Okay, so there's something called the Hartree-Fock limit in these calculations. So like I said, Hartree-Fock is the lowest ab initio level of theory, and it's missing some important interactions for the two electron integrals, which we'll talk a little bit more about. But this thing called the Hartree-Fock limit is where you have increased your basis set, and it's as good as you're going to get for the energetics at that level of theory. This should be a delta. Let me fix that right now, if I can. There we go. There we go. Okay, so the Hartree-Fock limit is as good as it's going to get, even if you use a really large basis set. So it's what's called reaching the basis set limit. So this table just shows going from DZ, TZ, QZ. Remember, this is our terminology for the basis set size: single zeta, double zeta, triple zeta, quadruple zeta. Okay, pentuple, sextuple. There's very little change from 5Z to 6Z. Okay. But the experimental is 141 for this bond association for hydrogen fluoride. Okay. Hydrogen fluoride bond association and bond association in general includes something called electron correlation. There's a lot of electron correlation energy when you are dissociating bonds. So, sorry. So this is as good as it's going to get for Hartree-Fock theory because it's missing this all-important electron correlation. So one nice thing about Hartree-Fock theory is that it is what's called variational. So with variational, you know that the Hartree-Fock energy is always going to be greater than or equal to the true energy of the system. Okay, and that's a nice property because you know you haven't gone below the true energy of the system. Okay, so if you increase your basis set size and the energy goes down, okay, as long as the energy continues to go down, you know that you are achieving a better representation of the wave function. The other property that Hartree-Fock has is it's size extensive. So that means if you take the energy of A, molecule A, at non-interacting distance with another molecule A, so at a very, very long distance where there's essentially almost zero interaction, you should get the same energy to within the precision of the calculation as if you calculated them separately. Okay. And this is important when you're looking at reaction chemistry, okay, when you have two molecules coming together and reacting. You want the cancellation of errors, and the only way that you can get cancellation of errors is if it's size extensive. You're incorporating the same amount of information, especially with the 2-electron integration, for both sides, okay, when you're bringing these molecules together. Okay. The problem is that it neglects this thing called instantaneous electron correlation. Okay, that's not included with Hartree-Fock level of theory. And the instantaneous electron correlation is normally very important for the quality of the results. Okay, so you generally don't see a lot of straight Hartree-Fock calculations in the literature anymore, but what you will see is inclusion of Hartree-Fock exchange in density functional theory. Okay, so it's still very relevant to understand what Hartree-Fock is, and you will see it in that manner in the literature substantially. So we will revisit Hartree-Fock as part of density functional theory. Okay, so what is this electron correlation? Electron correlation is that the motion of the electrons are correlated. So remember, with Hartree-Fock theory, you have this electron, it's seeing a smeared out cloud of all of the other electrons in simplified terms. Okay, so to get accurate energetics, you really need this instantaneous correlation of the electron motion. Okay, so the important one is going to be the Coulomb hole. So the Coulomb hole is you have 2 electrons that are in the same molecular orbital, one spin up, one spin down, and they want to stay away from each other. So their motion is correlated. But since Hartree-Fock does the smeared out cloud, it doesn't have that. What Hartree-Fock theory does have is the Fermi hole, which is when you have 2 electrons that are spin up, they're going to have to stay away from each other to the effect that they don't violate one of the quantum rules. Okay, so there is some electron correlation for the spin up electrons, but there's no electron correlation for the electrons of opposite spin. Okay, and that has an important consequence. What that means is that Hartree-Fock is always going to favor the high spin state. Okay, so this is the important part about talking about Hartree-Fock theory. If you're looking at molecules that have different spin states and you want to know whether or not the higher spin state, more electrons unpaired, is more stable than the lower spin state where you have fewer electrons unpaired, Hartree-Fock theory alone is always going to favor the high spin state. And that's because of the inclusion of the Fermi hole, but not the Coulomb hole in its calculations. Okay. And this will also have a consequence when you perform DFT calculations that include Hartree-Fock exchange. So we will revisit this in the afternoon lecture when we talk about density functional theory. Okay, so how do you include electron correlation for electrons of opposite spin? You have to do something called a post-SCF calculation. Post-SCF, like Møller-Plesset, perturbation theory, configuration interaction, coupled-cluster, or density functional theory. Okay, those levels include this electron correlation, the Coulomb hole. Okay, so just real briefly, perturbation theory. Perturbation theory is where you start with the 0th order Hamiltonian and you add a perturbation on. Okay. Now in mathematics, perturbation theory, the perturbation is supposed to be small. In perturbation theory for the quantum mechanical calculations, the perturbation is actually quite large. The first perturbation is the electron-electron interaction term. Okay. Normally in the calculations, the only thing that is corrected in perturbation theory is the energy and not the wave function. There is a term to correct the wave function, but generally most packages are only correcting the energy and not the wave function. Okay. So first order perturbation is just Hartree-Fock theory in Møller-Plesset series. And the perturbation is the electron-electron repulsion term. Okay. You have to go to second order perturbation theory, Møller-Plesset second order perturbation, to incorporate the electron-electron correlation. Okay. So here is the second term where you're looking at excitations of the electrons out of the Hartree-Fock optimized wave function. It promotes the electrons and then it compares the energy. So you'll notice here in the denominator, it looks at the difference in energy between the excited state where the electron has been promoted and the ground state. Okay. And the closer they are in energy, the more it contributes to the stabilization. Okay, so this is sampling how much the electrons want to get away from each other. This is how it incorporates this dynamic motion, okay? And that's how it samples it. The problem with this is if you have an excited state, if you have an electron promotion that is very close in energy to the ground state, then you can get instabilities because this term will get very, very small, right? And so the overall term will get very, very large. Okay, so that's one of the fallbacks or one of the problems with perturbation theory is if you have low level excited states, then the perturbation theory tends to fail. Okay, and so this is true when you have this thing called multi-reference character, which is common in first row transition metals, radicals, things of that nature. Going to third order, you have these things called triple excitations. MP4 includes single, double, triple, and quadruple. I'm sorry. MP3 only includes double and quadruple excitations. You have to go to MP4 to include triple excitations where you're promoting 3 electrons. Okay, and there are a lot of possibilities for triple excitations. So these are very, very computationally intensive calculations and generally only apply to small systems. 4 or 5 atoms. If for MP4, you know, you would have a lot of trouble doing it for a very large system, okay? Or they would take a very long time, and by a very long time, I mean they can take a month of compute time, and they're not restartable. Okay, the one thing that we know about the Møller-Plesset perturbation theory series is that MP1 is Hartree-Fock. Okay, and remember this is variational, but once you go to MP2, that's going to be lower in energy than the Hartree-Fock energy. MP3 is going to be higher than MP2, but then past that, you just don't know, right? One thing about the Møller-Plesset series is that it's not variational. You can drop below the energy of the system, okay, the true energy of the system. It is solved non-iteratively, so because you're only promoting the electron and calculating the energy without re-optimizing the wave function. Okay, so it's non-iterative, but it is computationally intensive. The other thing I like to point out is in Gaussian 16, the core electrons are not included in the excitations by default, and that varies from program to program as to whether or not the core electrons are included in the excitation. Sometimes it's important and sometimes it's not. It really depends on the molecule that you're investigating. Okay, so Møller-Plesset perturbation theory, what you would like to see is that it converges, but most of the time it actually diverges, but you really don't know because it's hard to go all the way up to the higher levels of the perturbation theory. Okay, so like I mentioned, you can predict what's going to go between Hartree-Fock and MP2, that's going to go down, MP3 is going to go up. But what you would like to see is that it's converging to a value. But often you're stuck at MP2 or MP3 and you really can't get to MP4 or any of these other levels. So it's quite common actually that it does something along these lines. So while the Møller-Plesset perturbation theory can be very useful for checking results, generally you need to have some comparing results with some other levels of theory. You generally have to have some other data available to you to see whether or not it's giving you reasonable results across the board. Okay, so outside of Møller-Plesset perturbation theory, you can do something called configuration interaction to get that dynamic electron correlation. So the difference between the MP series and configuration interaction is that instead of just having these promotions of the electrons and calculating the energy without reoptimizing the wave function, it goes through a different way of promoting the electrons. Okay, so it has a different method of what electrons to promote. So for configuration interaction, it uses this excitation operator. If you did a full configuration interaction, you would go through all possible excitations of the n electrons. Okay, so the 0th order wave function is going to be the Hartree-Fock wave function. You go through all the single excitations, all the double excitations, and then on top of it, you have this coefficient that goes in front of it that's optimized. Okay, so these are what are called configuration state functions. So whereas with the MP series, you promote the electron, just calculate the energy. with configuration interaction, you promote the electron, and then you also optimize a coefficient in front of it to determine how much it contributes to the overall wave function. Okay, so you have these extra terms that need to be optimized. So full CI, doing all possible excitations, is usually out of reach. So we do something called truncated CI. CIS is useful for excitations. We'll talk about that tomorrow. Doesn't contribute to the overall energy of the system. Okay. CID would be just doing double excitations. CISD, single and double. CISDT would be going through triple excitations. So if you do full CI, it's both variational and size extensive. But like I said, normally it's computationally out of reach. Okay, it would never finish. You don't have enough resources on the computer. So normally you're doing truncated CI. The problem with truncated CI is that it's not size extensive, but it is variational. So if you're looking at different spin states and you need some accurate numbers for different spin states, truncated CI may be a way to go, since you do have the variational principle implemented, but you cannot use truncated CI for reaction chemistry. It is not size extensive, it is size intensive. This is also solved iteratively, so you can get convergence failures because it has to iteratively solve for these coefficients. Okay. And again, core electrons are generally not included in the excitations in Gaussian 16. And like I said, that varies from computer to computer. Okay. So the main difference between the Møller-Plesset series and configuration interaction is that with configuration interaction, you're optimizing the coefficient in front of the excited wave function, whereas with the MP series, you're not. Okay, but that does mean it has to be solved iteratively. To solve the issue of configuration interaction not being size extensive, there was the development of something called quadratic configuration interaction. And what it did was it removed what's called the disconnected excitations so that it's size extensive. The problem with that is to make it size extensive, it loses its variational principle. Okay, so that's the main difference between the truncated CI and quadratic configuration interaction, is that you gain size extensive, but you lose variational, and it loses some electron correlation inclusion also. Okay. So you don't see QCI in the literature all that much anymore. You usually see coupled-cluster instead. Coupled-cluster is in the CI series, the configuration interaction series, but instead of using the excitation operator directly, it uses it in this exponential term. So e to the excitation operator. Okay, so it can be expanded like this. And if you did all of the excitations, then you would have, full CI. But we will be implementing truncated coupled-cluster theory. Okay, so instead of having the C coefficient that's being optimized, it's going to be the coupled-cluster amplitudes that are being optimized that go in front of these excitation wave functions. Okay, so the excitations that are included are different in coupled-cluster than they are in quadratic configuration interaction. Coupled-cluster generally includes more electron correlation terms than QCI does. Okay. Okay, so this is the overall equation, and you get the coupled-cluster energy. So again, you have to solve for these cluster amplitudes, so it's solved iteratively. And this is an incredibly intensive calculation. Okay, it takes a substantial amount of resources, disk, CPU, and memory. And generally, these methods do not parallelize well. They require a lot of communication with each other. So if you have experience with running highly parallel calculations, coupled-cluster has historically not been one of those that parallelizes very well. In fact, in the entire quantum world, they generally do not parallelize well. Okay? There are some codes out there that have the ability to run on a lot of CPUs, but you usually have to have a very large system to get any kind of good speed up across many nodes. And still, coupled cluster tends to not do well on many, many CPUs. Okay, so the full coupled cluster equation is generally out of reach, so we do truncated coupled cluster. The one that you'll see most commonly in literature is CCSD and CCSD parentheses T. Okay, so CCSD uses the single excitation and double excitation operator, again, in this E to the excitation operators. So it expands out in this way. Okay. The nice thing about this is it makes it size extensive, okay, but it's not variational. All right, so let me explain what CCSD parentheses T is, because CCSD parentheses T is considered to be the gold standard, okay? It's what you can calibrate against. But you want to be a little bit careful with CCSD parentheses T, because it's including triples in a perturbative fashion. So if you have something that has a lot of multi-reference character, those low-lying excited states, your CCSD parentheses T number could be worse than the CCSD number because it's adding them in perturbatively. And perturbation theory has a hard time with multi-reference character. Okay, so my suggestion is always look at both numbers. If you're going to do CCSD parentheses T, you should look at the CCSD number, and you should also look at the CCSD parentheses T values for your relative energies of whatever property you're looking at. If they are very close to each other, you're in a very good place. That is a strong indication that you've included enough electron correlation to get good results. If they differ substantially, and that word substantially is relative, it really depends on what you're looking at. If they vary more than you expect them to, that could be because there's multi-reference character, or that you need the triple excitations to include the appropriate electron correlation. What it means is that you're going to have to do more work. Okay, either you need some experimental data to confirm whether the CCSD or the CCSD parentheses T is more appropriate. You need to calibrate against something else. Maybe look at whether or not it has a lot of multi-reference character. Okay. Okay, so this is solved iteratively. Just like the QCISD and the configuration interaction and Hartree-Fock. Okay, so in summary for the ab initio series, for inclusion of electron correlation, okay, that dynamic electron correlation, Hartree-Fock does not include it. It does not include this dynamic electron correlation, which is normally very important for getting good quality results. Okay. MP2 includes it at increased computational cost. CISD has more. MP4 SDQ is pretty similar in inclusion of electron correlation compared to CCSD. MP4 would put just a little bit higher just because it includes more triples. Okay, it includes those triple excitations. And then CCSD parentheses T is considered the highest for inclusion. Now note that full MP4 includes more triple excitations than CCSD parentheses T. Okay. Making a note of that, for a lot of pieces of software, if you say that you want to do an MP4 calculation, it doesn't necessarily do the full MP4 calculation. It might leave out some of the triple excitations. So you want to check the manual to see whether or not it's doing a full MP4 or if it's just doing MP4 SDQ and leaving out the computationally intensive triple excitations. Okay. Okay, so the pros of the ab initio series is that there's a very nice hierarchy. So if you go up the ladder, you know that you're including more and more dynamic electron correlation. So if your value of interest starts to not change, then you know that you've included the electron correlation that is required for your system to get good quality results. Okay. The major con for the ab initio summary or series is the computational cost. Okay. These are highly intensive calculations once you move past Hartree-Fock theory. Now the computers have gotten much faster, algorithms have improved, so you can do much larger systems than you used to be able to. But it still takes substantial resources, especially for the CCSD parentheses T. Okay, so normally my suggestion is start small. Okay, start with a small system, get a feel for the kind of resources these calculations require. Okay. Okay, Oh, also the ab initio series tends to be highly dependent on the quality of the basis set. Now remember, one of the things that I said was the larger basis sets, that's more variables that you have to optimize. That means you have a larger coefficient matrix. Okay, so the larger your basis set, the more your computational cost goes up. Okay, so let's revisit the hydrogen fluoride bond dissociation energy. Remember that when we did the Hartree-Fock, we kind of maxed out close to this number, whereas the experimental is 141, so there was substantial error. So if you go to the MP2, you'll notice it drops below the experimental value, and that's because MP2 is not variational, right? MP2, MP3, none of those are variational. So then you see it starts to oscillate from MP3 to MP4. QCISD goes to 138, which is, you know, in between these numbers. And then CCSD parentheses T is at 140.6, which is approaching that experimental value, okay? So generally in the computational world, chemical accuracy is considered to be within a kcal of the experimental value, 1 kcal. Okay, so this is a table that just kind of gives a layout of computational costs. These are the theoretical numbers, the numbers without trying to impose any coding tricks to make the scaling better. Okay, so if you coded it in a very innocent way without putting any optimization in there, Hartree-Fock theory would scale n to the 3. And the n is the number of basis functions. Okay, so it would scale cubic. So I always like to say, if you double your system size or you double your number of basis functions, you don't double your computational cost. Okay, it goes up much faster than that. In reality, it's not really n to the 3. It's O n to the 2. Where you have a coefficient, some order that goes in front of it. So something closer to it goes up quadratically. Okay, so doubling your system size doesn't double the computational costs. Okay, quadruples goes up quadratically. Okay, so density functional theory is along the same lines as Hartree-Fock and computational cost. Okay, and that's why you see it so much in the literature. And like I said, we're going to talk about density functional theory and its forms in the afternoon session. Okay, so MP2 theoretically is n to the 5th. So we have a substantial jump in the computational cost, but the nice thing is it's not iterative. Okay, MP3, MP4 is n to the 6th. Okay, then you go to configuration interaction, coupled cluster, and you're n to the 6th iterative. Okay, so you also have to deal with the fact that you have to get convergence, so it has to go through cycles, and you have to wait for it to converge. Okay, MP4, full MP4 is n to the 7th. Okay, n to the 8th. CCSD parentheses T falls somewhere in this area. Okay, there's a single step at the end. That's about n to the 7th iterative. Not iterative, sorry. Okay, so you can see this is why you don't see things like CISDT and CISDTQ in the literature, because it's n to the 10th iterative. So you really can only apply it to very small systems. Okay, so I know I'm a little bit over, so we're going to work through this very quickly. I just want to broach the topic of single reference versus multi-reference. So single reference calculations is what we've talked about so far. Hartree-Fock, DFT, Møller-Plesset series, all of those are single reference. That means that you don't optimize a linear combination of wave functions. There's a single wave function that's optimized. With the Post-SCF procedures, like MP series and coupled cluster, you do have some excited state wave functions, but they're not optimized. Okay, so you have a single base wave function for the single reference methods. I did mention that first order transition metals tend to have a lot of multi-reference character. Multi-reference character is just where you have those low-lying excited states. Okay, so if you have low-lying excited states, that usually means that your overall wave function needs a linear combination of optimized wave functions to get good results. Okay, so it's not a single ground state wave function. The ground state, to get accurate results, needs to be a linear combination of optimized wave functions. Okay, and that's where multi-reference calculations come in. So we're just going to talk about CAS-SCF real quick. CAS-SCF is a linear combination of wave functions where both the coefficient and the wave function is optimized. Okay, but there's no electron correlation included. So you can think of CAS-SCF like multi-reference Hartree-Fock theory. It includes something called static correlation. That's the multi-reference character, but it doesn't include the dynamic electron correlation. Okay, so if you want dynamic electron correlation inclusion in a multi-reference calculation, you have to move to something like CAS-PT2, MRCI, or RAS-SCF. Multi-reference calculations are not for the faint of heart. Generally, what I like to suggest is if you're new to these types of calculations, you really need to collaborate with somebody who has extensive experience in running these calculations, or you need to run through some previous work to make sure that you can reproduce their results and that you understand how you reproduce the results, okay? Because there's a lot more hand manipulation when it comes to these multi-reference calculations that can substantially affect your results. There is a test for multi-reference calculation in coupled cluster calculations. It's the T1 diagnostic, and this is just an indication. It's not a you have it or you don't. It's an indication. So if the T1 diagnostic comes out to greater than 0.02, it might be an indicator that you have this multi-reference calc, and it might explain why you might be getting poor results. Okay, so that historically has been helpful in analyzing your system and results. Okay, so for molecular oxygen, one of the things I mentioned was molecular oxygen is somewhat difficult. You have the ground state, which has the 2 unpaired electrons. But if you have the singlet, you have a couple of choices. When you have singlet molecular oxygen, you can have a delta G or a sigma G plus, which goes to what orbitals are occupied. You can have a closed shell singlet or you can have an open shell singlet. Open shell singlets are very difficult because they're multi-reference problems. It looks very simple. You put an electron up here and an electron down here, but it's not a single wave function that contributes. It's a linear combination of occupations that make up the overall wave function. Okay, same thing here. Do you put it in this one or do you put it in this one? So in short, singlet molecular oxygen has strong multi-reference character, okay? But you'll notice that only this one, the sigma G plus, shows a value of over 0.02, okay? This one also has multi-reference character, but it only has 0.013, okay? So that's why the T1 diagnostic is an indicator, but it's not a definitive. Okay, and this is the last slide that I'll cover during the lecture. I have more slides. You can go ahead and look through them, but I want to cover what happens in a CAS-SCF calculation. So this is the complete active space self-consistent field. If you do a full CAS calculation, you would be doing a full CI calculation. Full CI calculation would be all possible excitations in all of the orbitals that are available. So the more basis functions you have, the more virtual orbitals you have, okay? And you would excite all of these and you'd optimize every possible combination, okay? Like I said, that's generally out of reach. So normally you're doing a restricted space. You have some kind of a choice of your orbitals. You choose occupied and the virtual orbitals that you're going to include in your active space. Now, how do you choose those? That's the tricky part. And this is why I say there's a lot of hand manipulation in these CAS-SCF calculations. So you really want to collaborate with somebody to begin with, okay? Or try to reproduce results in the literature, because the choice of the active space is critical. So normally you have a certain number of electrons and a certain number of orbitals, and then it does all possible combinations of occupancy in these orbitals for these electrons. Okay, so the terminology is CAS-SCF, electrons and orbitals. So this would be a 6-6, 6 electrons and 6 orbitals, and all possible combinations. Sorry, I was mistaken. One more. So this lays it out as to the configuration state functions that would be optimized. So if you were doing a 2-2, you have 2 electrons and 2 orbitals, you would have 3 of these wave functions that would need to be optimized, and this would be the overall equation. So the coefficient would be optimized and this excited wave function would be optimized. Okay, and that's the big difference between multi-reference calculations and the post-SCF calculations that do the excitations. In the post-SCF calculations, they don't optimize the coefficients for the wave function of the excited state. Okay, and this table lays out how many of these configuration state functions would need to be optimized. So for a 2-2, it's small, it's only 3. For 4, a 4-4, it's 20. You get up to a 10-10 and you have 19,000 of these wave functions that need to be optimized. So it ramps up pretty quick in computational cost. And remember, CAS-SCF is very much like multi-reference Hartree-Fock. Okay? Okay, so that's all I'm going to cover in the lecture. Let's go ahead and we'll take a 7-minute break and we'll resume at 11 a.m. Central Time. Central Daylight Time for the hands-on session. Okay, let's go ahead and get started with the hands-on session. So if you haven't done so already, please go back to your Vidi portal desktop, and if you don't have one already running, please launch a desktop. Okay, so if you go into your day 2 folder, you will see the lecture slides have been posted there, and there are the hands-on sessions posted there. So let's go ahead and go into hands-on session 3. Okay, if everybody could please indicate to me via a yes feedback that you are logged in and have access to hands-on session 3. I would appreciate it. All right, excellent. Thank you so much for the feedback. I do appreciate that. Okay. All right, so what we're going to do for this hands-on session is we're going to look at molecular oxygen. It's a nice small molecule, so it will run reasonably fast. But as I mentioned, it has a lot of quantum effects to it. It's high symmetry, it has unpaired electrons. So we're going to investigate the ground state and the first singlet excited state for molecular oxygen. Okay, so what I have listed here is the ground state, which is the triplet. Okay, there's 2 unpaired electrons. Like I said, we're not going to go into detail into these symmetry designations. There are resources that are available if you want to delve more into what sigma G minus means, but it goes to the symmetry. Okay, the symmetry of the orbitals, the symmetry of the overall wave function. Okay. So these are the experimental values for those, and then the singlet delta state is the one where it has the 2 electrons that are coupled in one of the single pi star orbitals, the antibonding pi orbitals. Okay, so the first thing that I'm going to have you do is just do a general Hartree-Fock and MP2 optimization on both the singlet and the triplet. Okay, and we're going to compare those results. Okay, so I've given you how to set up the input file. Remember, if you copy and paste, you're going to have those special characters in it. So you're going to have to remove the special characters, or you can type it in. Okay, so you can use NEdit to do that. So remember, Hartree-Fock does not include that all-important dynamic electron correlation, okay? But MP2 does. It includes double excitations to incorporate some dynamic electron correlation. So we can afford to do this. We're going to optimize the geometry of both the Hartree-Fock and the MP2 level of theory. Okay? And then we're going to use the MP2 optimized geometry to perform something called a single point energy calculation. So what a single point energy calculation means is that you are going to calculate the CCSD parentheses T corrected energy, but you're not going to change the geometry. Okay, so this is making the grand assumption that the MP2 optimized geometry is a reasonable geometry to correct the energy at the CCSD parentheses T level. Okay, and this is commonly done, and often this is a good assumption. Okay. One of the caveats of this is if you do not optimize a geometry at a level of theory, you cannot get the thermodynamics. You can't get the enthalpy and you can't get the free energy at that level of theory. Because to do the, or to get the enthalpy and free energy, you have to do a frequency calculation, and the frequency calculation has to be at an optimized geometry at that level of theory. Okay. Okay, so all we're going to be doing is correcting the electronic energy. Okay, and that's all the way at the bottom of the well. Okay, so we're going to take the MP2 optimized geometry. We're going to read that in from the checkpoint file, and we're going to correct the energy at the CCSD parentheses T level. Okay, and that's down here. Okay. Yes. So what I have you do is I have you create an input file for the CCSD T calculation. You'll notice I did not put parentheses in the file name. Can anybody tell me why I didn't put parentheses in the file name? Why I didn't call it CCSD parentheses T? Does anybody know? Why can't you? Right, it'll give an error because it's a special character. And in Linux, if you put special characters in file names, lots of bad things happen. Okay, so you need to stay away from those special characters. Minus is okay, underscore is okay, and equal sometimes is okay. But you never start a file name with a minus sign because then it thinks it's a flag. Okay, so this minus that I have in the middle, this dash, it's okay, as long as it doesn't start in the beginning. All right, so that's why I didn't put parentheses in the file name, and no spaces, goodness, no spaces. All right, so you set up this info file, and you'll notice I added the T1 diagnostic in there. Okay, but before we submit this oh, no. All right, can anybody tell me if they see something wrong with this input file compared to what we did yesterday? So I'm going to have to update this. I'm typing something into chat. But if anybody sees it, that's right. There's no path to the checkpoint file. Okay, so good catch. Excellent. So I forgot to add in the path to the file name. Okay, so what I put into the chat is that for all of these, you need to put that leading path in before the checkpoint file name. Okay. So I'll update the instructions, but if you go back and you open up your HS1 or HS2, take a look at that percent check line. If you leave it like this, you're going to lose your checkpoint file, and we need the checkpoint file. Okay, so make sure you add that leading path in for all of your input files with the percent check line. Very important. Okay, okay, so you need to make a copy of your checkpoint file. The reason we're making a copy of the checkpoint file from the MP2 calculation, which I have listed here, is because we're going to read the geometry in from the checkpoint file. So this MP2-1 checkpoint file has the geometry optimized from the MP2 level theory in it. We copy it to the CCSD T-1, and then we add in this geom equals check keyword. So it goes and reads it from the checkpoint file. Okay, that means that you will not have it in the input file because it's going to get the geometry from the checkpoint file. So often I will get the question, why don't you just call this MP2-1 up here if that's where the geometry is? Well, that would mean that you would overwrite your original MP2 file, and you don't want to do that because you want to keep those results from the MP2 result. Okay, if you put the MP2 checkpoint file name here, you'll overwrite it. So we make a copy of it, read in the geometry, and then it's going to overwrite it with the updated results. Okay. Okay, so one thing about CCSD parentheses T is when you do a CCSD parentheses T calculation, you don't just get the energy of CCSD parentheses T. You get the energy of MP2, MP3, MP4 SDQ, CCSD, and CCSD parentheses T. Okay, because it has enough information from the excitations to easily get all of those energetics. So when the calculation is done, you will have, and also the Hartree-Fock energy at the MP2 optimized geometry. So you will not only have the CCSD parentheses T energy, but you'll also have the CCSD, MP4 SDQ, MP3, and MP2 energy in the output file. Okay. Okay, so we do the same thing with the triplet. Again, remember, include the path in your percent check line. So this is now my way of seeing whether or not you're paying attention, to see if you include that in your input files. If you don't, you won't have your checkpoint file at the end. Okay. Okay, and then I just have you grabbing a bunch of the results. Okay, you can grab the T1 diagnostic, see what that looks like. If you set the input file up the way that I've asked you to, you should be able to grep the bond distances out. So you can compare it with the values, the experimental values that are in the table. Okay, can somebody tell me if the bond distance is going to be different between the Hartree-Fock and the MP2 calculation that I've asked you to do? Will it differ or will it be the same? Okay, so let me emphasize that. We're going to be optimizing at the Hartree-Fock level, and we're going to be optimizing at the MP2 level. So that means that the geometry is going to be updated. We're optimizing the geometry at the Hartree-Fock and the MP2 level. So they should have different bond distances. We're doing single point energy calculation for CCSD parentheses T at the MP2 optimized geometry. So if you pull the distance out of the CCSD parentheses T log file, will it be different than the MP2? You can just say yes or no. Okay, the CCSD parentheses T single point energy at the MP2 optimized geometry will have the same bond distance in the log file of the CCSD parentheses T as the MP2, because we're using the MP2 optimized geometry. We're only correcting the energy. So now let me ask, the distance between the oxygen atoms in the CCSD parentheses T calculation, will it differ from the output of the Hartree-Fock optimized geometry calculation? So for this one, yes, it will be different because we are going to be using the MP2 optimized geometry for the single point CCSDT, okay, not the Hartree-Fock optimized geometry, so they should differ. Okay, so then I have an optional exercise. If you have time and you're brave, you can go ahead and run through the multi-reference calculation. So this is optional, and it goes through running a restricted open shell Hartree-Fock calculation to get a starting wave function to do some CAS-SCF calculations. Okay. Again, remember to include the path in front of your file name for the percent check lines. If you don't include the path, you won't have the checkpoint file, and you need this to read in the wave function for the other calculations. Okay, so for the Hartree-Fock MP2 and CCSD parentheses T calculations that we're performing, you need the checkpoint file to read in the geometry. For the CAS-SCF calculations, you need the checkpoint file to read in the wave function. So you can also read in the wave function, And that is shown here, guess equals read. So if you put in a guess equals read keyword, it's going to read the wave function from the checkpoint file. Okay, so whatever result from the previous calculation that produced that checkpoint file. Okay, so that's about all I have to say about this assignment. So let's go ahead and get started. I'm going to go ahead and stop recording at this time. And if you have any questions or run into any problems, let me know. I am going to walk through some of the results from this calculation at 11:50. Okay, so I'm going to go over some of the results. You saw me typing in a bunch of commands while you were doing the hands-on, if you were still watching the Zoom session. So let me look at or show some of the results, and then we'll look at some of the files also. Okay. All right, so the first thing that I want to do is just pull out the bond distance. We did the Hartree-Fock for the triplet, right? Triplet oxygen, molecular oxygen is the ground state. Then we also did Hartree-Fock for the singlet. Okay, so this is the first singlet excited state, which has the 2 electrons spin paired in one of the pi star orbitals. Okay, and then we also did it for the MP2. Now, if you look at the bond distance and compare it to the experimental for the triplet, the ground state, Hartree-Fock, it's too short. Okay, it's definitely too short. And then for the MP2, it's too long. Okay, and this is very common. So Hartree-Fock doesn't include that all-important dynamic electron correlation, which is why the distance is too short. MP2 doesn't have a balanced amount of electron correlation. It's overshot, and that's why it's too long. Okay. And the same thing is true for the singlet. The Hartree-Fock is too short, okay, and the MP2 is too long for that first excited singlet state. Okay. So let's look at the energetics. So I pulled out the Hartree-Fock energetics. So I don't know if anybody saw me doing this, but one of the ways that you can pull out the Hartree-Fock result when you do Hartree-Fock calculation is by pulling or grepping for capital HF equals minus and the log file. This star just means it starts with HF minus and has whatever here and ends in .log. The problem is that pulls it from the archive. It's that block of information that's at the end of the log files. Okay. More often than not, it's split on lines. So this one is good. I can pull the energy here, but you'll notice this one is split on a line. So I've lost the rest of the energy. And remember that the Hartree is a very small number, okay? There's 627 kcals per mole. So you can't just take 1 or 2 decimal places. You need to take all of the decimal places that are provided you. Otherwise, it looks like the same energy. Okay, you're missing the accuracy. So instead, I put it through a loop, and I said, for file in Hartree-Fock.log, do grep this, done, for the file, and give me just the last line. Okay, so it just goes through and does those 2 and just gives me the last one. And this is the energy for the first one, and this is the energy for the second one. I'm actually not sure which one's the singlet and the triplet. And then I used the binary calculator and calculated the difference in energy. Okay, so I took the one energy, subtracted off the other energy, and multiplied by the conversion factor to get kcals per mole, which is what I provided here. So experimentally, the first excited state for molecular oxygen is 22 kcals up in energy. The Hartree-Fock number is 52 kcals up in energy, and that's a substantial error. And that's because of the missing dynamic electron correlation and the missing static correlation. Okay, like I said, molecular oxygen has strong multi-reference character, or to get it accurate, it has the multi-reference character that needs to be included in the calculations. Dynamic electron correlation will substantially improve that energetic, but to get much closer to the experimental value, you need to move to multi-reference calculations. That also include dynamic electron correlation, okay? Okay, so the other reason why this is so big compared to the experimental value is, remember that Hartree-Fock includes the Fermi hole, but not the Coulomb hole. So that means it energetically favors the ground state more than it should, because it has that Fermi hole electron correlation for the higher spin state, but not the lower spin state. Okay, and that's why the gap is even bigger than it should be. So the missing dynamic electron correlation and overstabilizing the triplet over the singlet because of the inclusion of the Fermi correlation in the triplet, but not in the singlet. Okay, so it's not as balanced as it should be. So that's why the Hartree-Fock value is so bad, okay, for these calculations. Okay, so this gives you a feel for, you have to move to these higher levels of theory to get better quality results. Okay, now how to pull the rest of the energetics. Most of those you can pull from the log file. Okay, so if you look at like the last 30 lines of your log file for the CCSD T calculations. Sorry. Okay. It'll show you the energetics in the archive. And this is the most straightforward and easy way to pull those numbers. Okay, so you can pull the CCSD number and you can pull the CCSD parentheses T number. If you have some scripting or programming skills, then you can write scripts to pull these numbers faster. Okay, otherwise you can always pull them from the archive, right? So you can pull the rest of the energetics and then see how much they improve the results as you move from Hartree-Fock to the higher levels of theory. So let's go ahead and do that for the triplet to singlet for the CCSD number. So I've got that one for that, and that one for that. Let me do it a little bit smaller. Okay, so there's the, clear my screen. Okay. So let's take a look at the, what's my other one? I didn't get enough. The quote was too big, sorry. Let me just try the, from the archive. Okay, so here's one other thing that you might notice is that in the Gaussian log files higher up, it will often list things that are exponential with a D. And that goes to the language that it was programmed in way back in the day. This is an E, but if you pull it directly and try to put it into like a spreadsheet, like Excel, Excel's not going to know what the D is. So you have to replace it with an E. Okay, okay, so here's our triplet. Let's go ahead and take this number and subtract it from the singlet. And we're down to 34 kcals. Okay, so CCSD parentheses T, that's a very high level of theory. Okay, and we used a reasonable basis set, CCPVDZ. That's a double zeta correlation consistent basis set. But we're still making a 10 kcal error in the excitation or the energy difference between the ground state and the first excited state for molecular oxygen. Okay, so we could do larger basis set to see if that improves the result at the CCSD parentheses T level. But the indication here is that it may be because of the lack of the multi-reference character inclusion, that we don't have the multi-reference character included in this calculation. Okay, and that would be the static correlation. So that's the optional part of this assignment if you would like to try your hand at that. But again, that gets you the multi-reference Hartree-Fock. result, okay, and leaves out the electron correlation part. Okay, so that concludes this hands-on session. I will stay online. If you have any more questions or are still performing calculations and have run into problems, please let me know and I will help you troubleshoot. Otherwise, we will resume again at 2 p.m. this afternoon to talk about density functional theory.